As stated, so I'm Dan Jaws. I'm a research fellow in UCL, and I've been working on this project along with some great colleagues. So they would be of Thomas, Devraj, who you'll hear from later on, Mose, Matt, and then the PIs on this project were Alex and Serge. So the project is entitled RADDISH. It's all about real-time data assimilation for digital twins, but where does the acronym come from? It's always, as comes with the territory, it's always a bit of a mouthful. So RADDISH itself stands for real-time advanced data assimilation for digital simulation of numerical twins on HPC. So in my part of this talk, I'm going to focus mainly on the data assimilation aspects, and then I'll touch on towards the end some of the high performance computing, so the HPC aspects. So just to begin with, I want to give motivation for the data assimilation and why it's needed, why it's used. And in most of my kind of setup here, I'm going to use the numerical weather prediction as the kind of test case or the example case to illustrate some points. So in essence, data assimilation is used a lot in state space estimation problems. So this is a case where you have, say, for instance, two complementary sources of information, but they are incomplete or inaccurate. So in the case of, say, numerical weather prediction, you have your observations, which are, say, sparse in a sense of the atmosphere. And then you also have your numerical models. So that's your your physics-based model, which will be solved on your high-performance computing system. So both of these two sources of information, well, the observations are incomplete in a way. They can obviously also have some inaccuracies. So you have some observation errors and so on. And then on your model side, there's obviously some inaccuracies as well. So you make some approximations in the physics equations or the parameterizations used. So the main use of data assimilation in this case is to try and use both these sources of information and marry them together such that you get the best estimate of your state space. So once you have your best estimate of your state space, so i.e. your atmosphere, you then use that and feed that back into your numerical model or your physics model to then forecast forward in time. So just again to highlight these, it's a sparse observation setting. So again, we can't really necessarily use a data-driven approach, just pure data-driven approach. But again, to get your head around it, in a numerical weather prediction, when I say sparse, we still have on the order of, say, 10 to the 7 observations, and your model dimension may be on the order of 10 to the 9. So it's quite a big problem in that regard. So just to put a bit of mathematical framework on the exact setup that we've been looking at within RADDISH, I provided some of the mathematical definitions that we're going to assume. So this is obviously going to be forecasting forward in time. So it's in essence, the data simulation is like a predict and a correct state steps. So you have a state vector, which is denoted here by X. So that state vector in a numerical weather prediction setting will be, say, for instance, your surface pressures, your wind velocities, your temperatures, and so on. You'll have a forward model, which is denoted here by capital F, and capital F will take your best estimate of your state at a previous time step and then integrate it forward in time. So that would be your forward model. This forward model, we'll also have some kind of model noise as well associated with it. And we're assuming that the model noise is normally distributed with some mean and covariance structure. And then on the other side, you'll have your observations. So the other source of information, which is your observations, which is denoted here as Y. So Y of t. So again, you'll have an observation operator, which is denoted here by capital A. And then you'll also have your observation noise as well. So the ultimate goal of the DA or the data simulation is to, in the particle sense, will be to try and reconstruct your filter and distribution. So you want to construct your distribution of your state space, giving all the previous observations. But one thing I want to emphasize on this slide is the capital F. So capital F is your forward model. And in our software package that we've developed, we've paid particular attention to this and made sure that the forward model is in the software package. We're agnostic to the forward model. So essentially, this could be any PD that you will plug into the software itself. So then, as I was saying, data simulation, it's been a while. It's been around quite some time. It's quite popular, obviously, in numerical weather prediction, and there are different data simulation techniques. So popular ones include variational techniques, so your 4D vars and so on, and your Kalman filters. These techniques are obviously very useful and have been used quite extensively and still are in operational settings, but they do have some difficulties, and it's been highlighted that they have difficulties in highly nonlinear dynamics, so highly nonlinear PD systems, and they can also fail to sometimes represent accurately uncertainties on your estimates. So on the other side, we have particle filters, and that's obviously the technique that we investigate here in our project. And essentially, particle filters offer this promise of fully nonlinear data assimilation, but they are known to exhibit difficulties in, say, for instance, high dimensional settings. So you have the what's known as the curse of dimensionality, but recent, say, computational advances and proposal techniques are aimed at addressing this. So we've, just to kind of give you an idea, very much an overview of this particle filtering algorithm, so not going into too much detail. I've kept this quite generic. So essentially, you'll have your particle filtering. So you'll have your particles. So again, don't get confused here. Particles is just the terminology, but you can think of a particle as like an ensemble member or a sample. So you'll have your ensemble member or your particle. You'll have associated state space for that particle. So some sort of vector of, denoted as X in the previous slide, some state space vector for each particle. This will be updated forward in time given your forward model, your capital F. So that will be updated to Tn+1. We then can use various different particle proposals. So you're not necessarily tied to just using the what's known as the bootstrap filter, which is just using the updated particle states and using that as your proposal distribution. You can use some smarter techniques, and one of the other techniques we use here in our case is called the optimal proposal, which will essentially condition the updated states on the observation themselves. And then once you do that, you have to get the observations of the true state at the Tn+1. So this comes from your ground truth model. So this could be in numerical weather prediction, this is coming from your actual observations of the atmosphere, whereas in some of these numerical experiments we've been running, they're coming from what we denote as our ground truth model. So we observe the ground truth model at discrete points within the domain. You then get the associated synthetic observation from the particles at the exact same locations. You then can calculate some particle weights. So the weights are going to be denote how close certain particles are to the true state. So good particles will have higher weights and bad particles will have lower weights. And then there's a resampling step. So this is a very important step within this particle filtering algorithm. We're going to resample the particles. So we're going to keep the good particles, keep the higher weighted particles, and duplicate them and copy them. And we're going to delete the bad particles. And we also in this step say for instance, produce statistic estimates of your mean and your variance and so on. So that's generally just the particle filter algorithm itself. So now I'd like to just run through just a quick kind of interactive notebook, so to see this in action. So what I'll do is I'll just exit out of that and go to my browser. So this is just an example for this tsunami example. So hopefully again now everyone can see my window here. So essentially what we have is this is what we are kind of calling our hello world example within the particle DA package or the software system. and it essentially solves the linear shallow water equations. So the linear shallow water equations are going to form this forward model f of x of t. It's inbuilt within the platform itself, so it allows you to kind of play around with the different particle proposals and so on and so on. It solves the linear shallow water equation as it just said, and it uses a first order finite difference scheme. So it's based on code base already on GitHub. It should be qualified here at this point that this kind of technique would not be sufficient in an actual real world Tsunami simulation, but nevertheless, it's a good toy example. So the linear shallow water equations are denoted here. Essentially, you have a conservation of mass and then a conservation of momentum equations. We're going to have 3 state variables. So we have our free surface elevation, our wave height denoted by eta, and then we have our depth average horizontal velocities u and v. So just as a kind of, again, as a toy example, we have a square domain of 200 kilometers by 200 kilometers, and we're going to integrate this solution for 1,000 seconds, and we're going to simulate observations at various observation locations every 5 seconds. And the initial condition is just a Gaussian shaped wave in this bottom left-hand corner. So you'll see here that this is the true ocean surface height. So this is what we're going to be aiming for in our simulated mean estimates of the ocean height. So the true surface at times equal to 0 is just this Gaussian wave at the bottom left. So you can think of it as just a hump on the ocean surface, and then the rest of the ocean at present at the very start is just flat. But so as this progresses in time, so as I move this slider, we see that the wave will now propagate from the bottom left-hand corner to the top right-hand corner. And as denoted by the red stars, they're the observations locations. So we're going to be extracting the wave heights from those observations locations, and that will influence our simulation schemes. So the wave propagates from left to right, and then goes all the way up to the top right-hand corner. So again, it's very much a toy example, but it'll showcase some interesting features. So one of the things that should be noted, there's 15 observation locations. We initialize an ensemble of 200 particles. So there's 200 particles, and the initial conditions of each particle is essentially based on a prior that we're saying that the ocean surface is flat. So the initial, we have no observations of a tsunami wave that haven't occurred until it actually hits some of these observation locations. So if I run this, and in the interest of time, I won't do it on screen, but if I run this toy example here on my laptop, it'll take, say, for instance, around 40 seconds. And then if I load in some of the outputs, which I've already done, we can see what happens here. So this is, just to spend a bit more time on this, on the top left, this is the true ocean surface height. So again, this is the plot that I've just shown you. So this is what we're aiming for. On the top right, we have the assimilated ocean height. So again, at the initial t is equal to 0, this is essentially a flat ocean. And then we have some standard deviation of the ensemble of the particles themselves, and then just an absolute error. So if I let this play through, we see that as time progresses and as the wave starts hitting some of these observation locations, our simulated ocean wave height starts to match the true ocean surface height. So as the wave propagates up, and then you can see the standard deviation obviously is kind of minimal, closer to the observation locations themselves, and yeah, and then the error obviously is on the bottom right. So if I just kind of skip towards the very end, we see the very end, the resultant wave height. So again, there's no other information going into these ensemble members or these particles other than the fact of the observations at these locations. And at the very end, we kind of have a good representation of the true wave height. So one of the things we can look at here is also the particle weights. So as I said, there's 200 particles in this example. And initially, they're obviously initialized with all the same particle weight. But as time goes on, we see that different particles will have different weights, obviously and the weights are calculated based on the observations themselves. So you can see that in this case, we have quite a good performance, because what we do not want to see is what is denoted as particle degeneracy. So particle degeneracy is where, say, for instance, one particle will have quite a large weight and all the other particles will be very low weighted. And essentially then once we do the resampling step, that highly weighted particle will then just be copied, and essentially we'll get degeneracy in our particles in our ensemble. So we see quite a uniform weights as we go through time. And this is also highlighted here in this estimate of our ensemble size. So we're, as I said, there's 200 particles and we have roughly an ensemble size of 200 across the course of the simulation. So that's just a quick demo of the toy example. So now I'm going to return to the slides. So apologies again for this jumping back and forth, but hopefully you can see the slides again. So now moving to one of the things I was trying to pay particular attention to earlier, which is this forward model. And I mentioned the fact that our software package, particleda.jl, so it's a Julia framework, is developed to be a forward model agnostic. So to showcase this generality, we've also integrated this particleda system with a pre-existing forward model, which is called SPEEDY. So SPEEDY is simplified parameterization's primitive equation dynamics. It is essentially a simplified atmospheric circulation model. So it's a bit more complex than the Tsunami model that we've just showcased or just seen. But to give you some idea of what SPEEDY is, so as stated, it's a spectral primitive equation dynamic core. So primitive equations are used to simulate the atmosphere, and it's similar in essence to the current state-of-the-art atmospheric general circulation models, but it requires drastically less computational resources. So this is used a lot and was developed pretty much primarily with the idea of running large ensembles and or say data assimilation techniques. So it's not used in practice or in an operational case, but it is used to kind of run and see what happens when you run quite large ensembles, because it requires a lot less computational resources. So as I was saying, so there's going to be some software considerations that we have to take into consideration, because SPEEDY is a pre-existing model. It's also written in Fortran, whereas our particleda code is written in Julia. So we have to now start to consider, well, how do you integrate with external models and so on. So this, if someone wanted to use particleda, you would have to go along similar steps like this. So the software considerations are mainly, say, for instance, data transfer between the codes. So you obviously have SPEEDY in Fortran, and you have the particleda code in Julia, and you'll have to transfer data from one to the other. And then also you're going to have to figure out a way of calling the SPEEDY model itself from Julia, from the particleda code. So we've successfully done that in this case, and the setup of the data assimilation experiment that we're running is just going to be is highlighted here. So essentially, just to again emphasize that SPEEDY is a lot more complex than the Tsunami model. So we have a greater number of prognostic variables in this case. So SPEEDY will consider the velocity components, the temperature, the specific humidity, and the surface pressure. We also have a three-dimensional grid in space. So we have, it's a very coarse resolution for the whole globe, but we essentially have 96 grid cells in the longitude, 48 in the latitude, and then 8 grid cells in the vertical. The initial conditions for the particles, which we're going to use in the data assimilation experiment, are coming from randomized states of the atmosphere. So we're not, say, for instance, our prior in this case is just a randomized atmospheric states instead of atmospheric at 0, which would be what we used in the Tsunami case. We have 416 observation stations. So these are denoted here on the map on the bottom right as the red stars. The location of these observation stations are going to mimic, say, for instance, where weather balloons or radiosonde data is actually obtained. So there's a greater concentration of the stations on land as compared to over the ocean. And we're going to simulate the surface, just the surface pressure now. So just to simulate the surface pressure every 6 hours. And the total number of particles we need to run are 256. So as you can see, so the two plots, the two movies. So on the top here, we have the percentage error of the surface pressure through time as we run this. And on the top right, we have the standard deviation of the simulated pressure. What's quite interesting, obviously, is the standard deviation closer to the observation locations is a lot less than away from it. And so that the black dots mimic the location of the observation locations. And then in the bottom left, we have percentage error of the simulated temperature. And then on the bottom right, we have the standard deviation of the simulated temperature. So you can then start looking at, instead of just these kind of movie plots, you can start looking at, say, root mean squared error plots of the surface pressure, specific humidity, temperature, and velocity. But I'm not going to spend too much time on that, because I want to now just emphasize the H in RADDISH, which is the high performance computing aspect. So this was a big drive of this project, was to develop the software such that we can deal with real-time data, and we can scale this software, and it's optimized to use high performance computing systems. So the tech stack we've used is obviously GitHub. Julia is the main program language, as I mentioned earlier. So Julia is offered, obviously it's relatively new, it's been around quite a while now, but relatively new program language, but it offers this kind of readability and usability and code development, ease of code development, but also on the flip side, this high performance computing aspects. So we picked Julia as well. In a way, it's also easier to integrate with, say, for instance, pre-existing models that external groups might want to come forward with. And then from the kind of HPC aspect and the parallelization aspect, we're using MPI. So MPI obviously has been around quite a while, but it still does a very good job. And then for IO, we're using HDF5. So just to recast your mind back into what the particle filter algorithm does and how, say, for instance, we're going to actually parallelize this. So in most of these steps, we can actually run this in complete parallel. So we can update the particle states in parallel. They're completely independent tasks, particle proposals, get the observations, synthetic observations, and even calculate the weights. So all of these tasks can be completely parallelized. The only communication step is going to fall into this, the resampling step. And then also for, say, for instance, the MPI gather steps to try and calculate the statistics. So this is the kind of the bottleneck for performance is this communication step. So we've used two types of parallelization, so both shared and distributed parallelism. So we can split the particles up across various MPI ranks. This offers kind of a constant memory footprint when scaling up, so you can just load each rank with more particles, or sorry, add more ranks, and it gives an approximate linear cost increase in the state vector dimension now. So once we start doing the MPI gather and collects, that obviously the cost does start to increase as the state vector dimension increases. Then from the shared parallelism viewpoint, we can use threads. So obviously for the particles that are located on the same MPI rank, we can then parallelize them on using threads, and this is implemented in Julia using the @threads macro. And then for the MPI, we can loop across the particles in the various nodes, and this is implemented using the MPI Julia package. And again, the communication is where the performance bottleneck will arise. So just kind of give you again a brief overview of the parallelization that's implemented. So we have in this example, we have 4 ranks, and to keep it simple, in this example, each rank only has one, say for instance, state vector, so it's denoted as X, and then we're going to update that state vector X given our forward model. We're then going to calculate the weight, so we get the W, and each of these can be done in complete parallel on different MPI ranks. We then have to gather these weights, so we have to gather the weights to then compare the weights and so on. So that's going to be an MPI gather. We then resample these weights. So as I stated earlier, we're going to keep the good particles, so the higher weighted particles, and get rid of the bad particles, so the lower weighted particles. And then we're going to broadcast these weights back out to the various ranks. We then have to copy and receive various the state vectors associated with the various indices that we're going to keep, and so on, particle indices that we're going to keep. And then when we want to do, say, for instance, the various statistics, so calculate the mean and variance and so on, we're going to have to reduce it back to the master rank as well. So that kind of gives you an idea of just the parallelization that's implemented in the framework. To showcase some of the parallelization and how it performs, I will preface that these are kind of older results, so we're still working on the newer scaling results, but this was done on a KNL partition, and it's also done with Julia 1.4, so we now run it with Julia 1.7 and so on. But I'm not going to, again, spend too much time, but as we increase the number of ranks from 4 to 256, at 256 ranks, we're using 4,096 cores, and we're simulating 260,000 particles. And we keep the parallel efficiency. Obviously, the goal is to stay close to 1, so we keep it close to, say, 90%. So where does the performance degrade? And as I was alluding to earlier, it's in these MPI gather and collective calls. So the MPI gather here is denoted by purple. And as we increase the rank on the x-axis, we can see the purple line, the runtime for the MPI gather drastically increase, whereas most of the other function calls keep quite consistent runtimes. So that's just a kind of an overview of the high performance aspects. So again, just to kind of conclude my section, whereas you'll hear from Devraj some other aspects that are being developed within RADDISH. So the particle filter and data assimilation has been implemented within, say, user-friendly software platforms. So we denote it as it's called, particle DA. We've put a lot of emphasis onto ensuring the applicability of the platform. So emphasis on numerical efficiency, scalability, and the optimization for HPC frameworks. As I've tried to emphasize quite a lot, the platform is developed to be forward model agnostic. So we want to make sure that it is applicable to a wide range of modeling settings. And in this case, I've just shown some results with a basic Tsunami model and the simplified atmospheric model. So for our future work, we're looking maybe perhaps to extend the optimal filter to, say, unstructured meshes, that sort of thing. And then we're also, the current state of the art, I suppose, is to couple the particle filters with, say, localization features. So you've got the LETKF DA techniques and so on. So we're looking at perhaps implementing those. And then on a usability side, we really would wish and hope that this platform's uptake is used by a broader audience. So we're going to try and support the uptake with other users in different modeling settings. So that's kind of it for me. So you'll hear from Devraj now. But yeah, so thank you for listening. Look forward to any questions you have. Just stop sharing now.
Yeah, thank you, Daniel, for that presentation. Okay, so just let me share my presentation. Okay, so thank you all for coming and listening to the talk. The presentation that Daniel gave is about particle DA. It's already ready to be deployed, and it's working fine with 2 kinds of models. If any of you would like to collaborate, please get in touch with us. This presentation that I'm going to talk about is about a small add-on to the particle DA. Particle DA works good, sparse observations, large systems, But is there any way we can increase the efficiency or the speed of the particle DA method? Daniel, just to check, is my screen okay?
Yep, I can see your screen fine.
Yeah, this work is joint with Maria and Serge. Serge is a PI on the project RADDISH, and Maria is his PhD student. So if there is one take home from this presentation, it's going to be that use the effect of parameters in a system to nudge the data assimilation process. So what Daniel was showing was use the observations and assimilate them to move the system forward, to predict efficiently. What I would say is this presentation talks about the use of parameters, which has been ignored for many of the data assimilation problems. So one of the factors, parameters encode useful information regarding state evolution. For example, for mechanical problems, it would be inertia, stiffness, damping ratio. It could be the initial parameters for evolution of a model. In this case, for Tsunami, it is something like that. So the aim is to jointly estimate the state and parameters so that the DA can get a little bit push. And I'll show it for one of the very simple problems that the push is quite large, and it can actually give large gains in ensemble size, reduction of the ensemble size that we use to run the model, and also faster convergence. This is planned to be added to particle DA. For example, now for the time being, it's only in MATLAB. So the problem that we are going to see is this. On the left side, you can see a big red dot, which is the initial swell in a tsunami. So tsunami happens because there is a swell in the sea, and under the influence of gravity, when the swell drops, it creates waves. In the blue dot is the sensor which picks up the tsunami signal. So these sensors are usually deep sea sensors. There are sensors also near to the coast so that we can know when the tsunami is coming. So as the tsunami propagates, the swell has fallen into the sea and the waves are being generated. And on the right, you see what is the wave that the sensor picks up. So this is the model that we will use to compare and to do to the data assimilation. Okay, yeah. So you have a peak and you have a swell, and after some time, the value at the sensor reduces. Okay, so there have been recent works which have used some kind of Kalman gain, optimized way, reduced order, but all these problems need a dense tsunameter networks or the sensors that you saw. And they also need a requirement of a large ensemble size, usually hundreds or more than that. And they do not use tsunami source parameters in the assimilation. Now, I will demonstrate this using two examples. On the left is one tsunami source with one sensor. And on the right is another same tsunami source, but 36 sensors. So we are going to compare the performance of the system on the left and on the right. Now, it would seem intuitive that since you have a lot of sensors, the system will work better, and it should actually. But for comparison, I have taken a case in which the data assimilation uses only one sensor and 36 sensors. So the comparison is with ENKF, which is ensemble Kalman filter, very commonly used for data assimilation. And the blue is the value at the sensor, the real or the simulated wave at the sensor, and the orange dots are the assimilated wave. So with the simple ensemble Kalman filter, even if I use an ensemble size of 136 sensors, the algorithm is not able to pull the orange wave towards the blue. There is still a lot of error. One of the reasons is because the size of the state is quite large, around 20,000 state variables have to be updated using these sensor values. But on the other hand, if I use a an ensemble Karman filter, same algorithm, but include a parameter evolution in it. In this case, the parameter, as I said, is the initial height of the sea swell. So if I include that into the same algorithm and let it evolve along a Brownian motion, I can share the mathematical at the end. We see that the orange wave, the assimilated wave, quickly latches on to the real waveform. So at the left is the simulated waveform. In the middle is the assimilated waveform once it has passed through the algorithm. And on the right is the error between the simulated and the assimilated. Ideally, we would like the error to be as low as possible. So you can see the shape of the tsunami wave on the left. It's evolving. Once it hits the sensor, you can see in the middle, the assimilated waveform slowly picks the shape of the tsunami wave. This is only because there is a parameter evolution which helps the data assimilation to latch on to the system's evolution. And slowly as you go on the right, you see the error has reduced to nil. So this works. If I run the same with an ensemble Kalman filter for an ensemble size of 5 or 10 or even up to 100, the system does not, the data assimilation does not progress nicely. It actually fails after some steps. But just with an ensemble size as low as 5 and just with one sensor, if I use the same algorithm but include a parameter evolution, the system works quite remarkably well. So here I show the evolution of the parameter. The left is the simulated wave. In the middle is the assimilated wave and the simulated wave. And on the right is the parameter evolution. The value of the parameter is 1. So you see slowly and immediately the parameter picks up to the value of 1 and it stays there. And that's the reason why the orange waveform in the middle latches onto the blue waveform. So just by changing, so what the motivation was to somehow increase the efficiency of the particle DA. And this was one way we could find, especially for a tsunami model, we have a parameter. For models which don't have a parameter, it's difficult. But most of the models, PDEs, have coefficients which are unknown. If they are known, well, this method is not applicable. But most of the PDEs also have forcing functions. In this case, the initial swell in the ocean is a kind of forcing function or an initial condition to the nonlinear shallow water equations, linear shallow water equations, or for nonlinear also. Just by including that parameter, we are able to see so much difference in the data assimilation. So before it has to be included into particle DA, now it works with one parameter. We have tested it with multiple parameters, but we find that it needs a bit more tuning. So this is an add-on to particle DA, and it increases the speed and the speed of convergence as well as the number of the ensemble size. But we have also incorporated Langevin-assisted parameter dynamics, in which the evolution of the parameter is not along a Brownian motion, but along energy surface, and the movement is controlled by Langevin dynamics. So this is still in the workings, and we expect to finish it so that it can be incorporated into particle DA. So the applications are PDEs with constant coefficients, constant parameters, or constant forcing. We're still working on if there are variable coefficients or if the forcing changes with time. So this is the standard process dynamics equation. X is the, as Daniel said, I think it's a very similar equation. X is the state of the tsunami model, which includes the height of the tsunami wave and the velocities in the X and Y direction. F is the model, the numerical model, which runs a tsunami. Sigma X is the process noise, which has to be tuned. And V is a drift. The measurement is the height of the tsunami at the sensor. And sigma Z is the measurement noise. And the measurements are collected like this if there are more than one sensor. The only difference is to include a parameter. So just by including a parameter in the dynamics and in the update of the Kalman step, we are able to see the difference in the behavior. Yes, thank you. With that, I finish. It was a short presentation. Thank you for listening. I remove my share now.
Great, thank you, Dan and Devaraj. I see Penelope has a question in the chat, and I'll go ahead and read that off. But first, I just want to say if anyone wants to ask a question, we'd love to get a discussion going. So please feel free to request to unmute and ask your question live. That'd be really nice, or start to put some questions in the chat. So Penelope would like to know, do you have any advice for good resources to learn about approaches to building digital twins in general for people who are new to the area of research?
Okay, so yeah, maybe I'll take that, but Devaraj, obviously weigh in if you have any other recommendations. I think it's so digital twin in a way. For me, I feel like it's not even, we're not settled on a definition of digital twinning either. But for me, so what we've presented is, say, for instance, is one facet of digital twinning, which is the data assimilation. So you want to simulate real-time data into your model. For me, my understanding for digital twin is then you have to kind of close that loop with an action step. So you have to obviously act on this kind of assimilated model state. So to give you a resource on it, I'm not 100% sure, because I think there's so much resources in different, it depends on what field you're in, I suppose, and what aspects of digital twinning you want to look at. So I don't have a resource off the top of my head, but I think it really depends on what domain you're kind of thinking of developing a digital twin within. So yeah, sorry about that.
Yeah, thank you, Dan. Thank you, Penelope, for that question. Digital twins, I think, is a very broad name. Maybe you're already familiar. It includes basically running the modeling of a system, simulating it, getting data, assimilating, and predicting to see if it matches with the real observations. A very, very broad definition. But the digital twin, I think there are projects in which they have their own definition of the digital twins. So if you want to learn about data assimilation, I think you can go to, which I have found very useful, is the training lectures and notes in PDF form from the Met Office website. And I'm not able to get a link now, but I can share in the chat in some time. They have very nice notes if you want to learn about data assimilation. And then from there, check what digital twinning is.
So someone put in the Google Doc, is there any Python-based implementation for RADDISH?
So there is not. So okay. So from the particle DA side, there isn't. So it's all written in Julia, but there should be. It should be quite easy to implement with a Python-based code or so on, because essentially that's one of the reasons why we picked Julia is to. So if you bring in your own, say for instance, forward model, your own PDE solver, and that's written, say for instance, in Python. The code base itself is kind of set up such that it can integrate with these external models. So if you are interested in integrating your forward model, your PDE solver within the particle DA, please do reach out to us. We'd love to hear from you, and we can hopefully work together on trying to integrate that together. So yeah, so I should have mentioned as well. So we have a very strong research software engineering group that have supported us. So that would be Thomas, Mose, and Matt. And so they're obviously the ones in charge of the software development, but very capable. So as I said, if you are interested in integrating with the model, then please do reach out, and we'd love to hear from you.
So in the Google Doc, you'll find contact info for Dan and Devaraj, as well as for the RAM team, the research application manager team at the Turing, and the partnerships team. So those are all, contacts if you guys have follow-ups, but we still do have a little more than 10 minutes if anyone wants to ask another question. So we have a question in the chat. Do you have any comments about how data assimilation may evolve to help in combining simulations with AI approaches?
Yeah, so I suppose this is obviously a massive area. So yeah, utilizing, say, for instance, AI trained models within your physics model or within the data assimilation step. So there are some very interesting packages out there, particularly in Julia for this, and integrating, say, for instance, ML techniques within, say, pre-existing, say, for instance, even Fortran or C++, numerical weather prediction models, that kind of thing. So yeah, in a way, there's a lot of considerations that do have to go into that, though, because if as soon as you start integrating ML techniques within, say, for instance, your physics-based model, and if there's any sort of feedback loops, instabilities might be generated. So there's a lot of thinking that needs to go into that if it's part of the assimilation or the prediction step. So it's a very interesting space, and there's ongoing work within our group looking at that as well. So yeah, I suppose that's my comment on it, but I don't have much else to add on it.
Dan, you had worked on this, right, for the cloud-based measurements. Was it half model, half learning, or is?
Yeah, so yeah, not fully integrated yet, but yeah, so essentially we're training a kind of an AI model to predict the convective available potential energy within the atmosphere to get kind of distributions on that value, and then try and feed that back into the numerical weather prediction model. So as I was saying earlier, you do have to consider quite a lot there, though, because if you nudge the simulation with the ML or the AI technique, it might cause instabilities and stuff like that, because it is within this kind of feedback loop. But yeah, ongoing work.
So we have a couple of questions relating to the real-time element in the title of the talk here. So different questions, though. So the first one is, the real-time element is between the physics and the particle filtering model, is a question. And are there plans to integrate in real time with the observation measurements? So maybe you guys can address that one, and then we have one more. You can read it in the chat too, if you if that wasn't clear.
Yeah, I'll just pull it up myself. Sorry. Chat. Okay. So yeah, from Blair. So so the real time, I suppose, is a kind of very much a prerequisite for the kind of digital twinning, right? So you kind of need this to be acting within a real time environment. So the emphasis for our implementation on the real time is to make sure that is the coding framework is optimized to its best extent, so that we can run this. So essentially, that the limiting factor is not going to be your computational runtime on this, and so we do want it to be able to run within real time. I'm not sure if that answers that first question, or Devraj, do you have anything to add to that? Okay, so I see thumbs up, so maybe that was good. But so then the second part, is there plans to integrate in real time with observation measurements? So yes, but this is what we've showcased already in my talk anyways, was with the Tsunami and the speedy model atmospheric, and our true observations were coming from a kind of a ground truth numerical simulation. So yeah, if you wanted to integrate this into, say, an actual numerical weather prediction, your measurements will be coming from the atmosphere itself. So that'd be something we do want to investigate and to go down that line perhaps, but at present we haven't done that. But the framework is there.
Yeah. Thank you, Dan. Thank you for that question. The question is, if you are running this near real time, how do you differentiate drift change in inferred parameter values from fluctuations noise? First of all, that particular add-on is not yet real time. It has to be optimized and included in particle DA. And second, how do you differentiate? We have to run this on a real model to see how the effect is. Most of the time, even with simpler algorithms, we have seen for this particular model for tsunami problems that the parameters don't change much. So the only add-on that the parameter estimation here gives us is an increase in efficiency and convergence. So yeah, thank you for that question. That's something we have to think about. Thank you for that.
Sorry, I'm trying to hop into the weird thing and inserted an email there, but Soma, I'm trying to answer. You can please email the RAM email address. So it's ram@turing.ac.uk. It wants to like put someone's email address in there, which I don't want to do. Okay, that worked. So basically, Jiri, thank you for sending that. Some more info that's helpful for the discussion. That's really great. And then Soma was asking about maybe a seminar or workshop to introduce the tool. And so I said to contact the RAM team, and we can help out organizing that if you guys are up for it. But that's exactly the kind of stuff we're hoping to kind of create these connections with this workshop. And then we have one last question. How do you characterize, propagate, and quantify uncertainties in temporal predictions of a phenomenon, given that observations, measurements aren't available uniformly?
So yeah, that's quite a great question, I suppose. I don't know, Devraj, do you have?
Yeah, Parag, thank you. I think this question comes from a perspective of sensor placements, I would say. And we don't have, well, Daniel's case, the sensors, especially if they are balloons or moving sensors, it makes a difference. Daniel, what about your sensors? Are they fixed?
They're fixed in location, yeah.
They're fixed, yeah. Yeah, and moving sensors, yeah, we have not yet tackled that. Sensors which are moving, especially for our case, the buoys, for tsunamis, the buoys and the dart sensors, which are deep sensors, they don't move. So, but yes, again, thank you for that question. It makes, we had a small project in which we wanted to optimize the location of sensors based on by optimizing the time taken to reduce the variance to acceptable limits, but we have not yet pursued that much. But that's a nice. Thank you for that question, Parag. Alden, there's one more question by Soma Chakraborty. Before that,
she was asking about maybe doing a seminar or workshop. Unless I think that's it. So if anyone else wants to ask a question live or in the chat, we have time for one more. Otherwise, we can wrap up early for lunch. So I think that's I think we can finish up. So thank you, Dan and Devraj. That was really great. And thank you to all of our participants. It's been nice to have you here, and thanks for your questions. And go to the Google Doc for contact info for the RAM team as well as Dan and Devraj. Thanks, everybody. Oh, we've got someone who wants to ask a question live. Okay, we're gonna let you in.
Thank you.
Sorry, I was trying to click all the buttons before you all left. Hello, I'm Jere, and thank you very much for your talk. It was absolutely amazing. I'm really interested, Dan, when you were talking about using the MPI and the deployment into HPC. Did you deploy to some local HPC cluster at your university, or did you use cloud deployments for your experiments?
For the parallelization experiments that I showed, the results were done on CSD3. So it's not a cluster in UCL itself. But no, we have not done it on a cloud base yet. And also I want to preface as well, the results I showed you were on a KNL partition, which we just used at the time because we had time left over on a KNL, but it's not optimal for what we wanted. So yeah, we're revisiting the kind of scaling plots and so on. So that's work in progress. But yeah, no, for cloud-based stuff, we haven't used it yet. But obviously, it would be a good avenue to go down if you are starting looking at this in a digital twinning setting and so on.
Thank you. Can I have one quick follow-up question? I promise I will just let you go for lunch. How did you find your workflow with Julia? And obviously, you mentioned also some packages which were actually in Fortran. I don't know. If you compare it with, for example, like Pangeo projects and the Python, C++ workflows, did you find the Julia better for your use case?
So Julia, we had a great benefit within our team is Mose. So Mose is one of the research software engineers, and he's actually heavily involved in developing numerous Julia packages themselves. So he's kind of a Julia wizard. So it was great to have him involved. With regards to the Fortran, Speedy is the atmospheric model that's written in Fortran and the one that we integrated with. It's developed kind of a way to do these data simulation experiments, and so it actually always reads and writes the file. So our only real difficulty with calling and integrating with the Fortran was reading and writing files back and forth. Obviously, it's not the most optimal, but then we could also call the Fortran executables very easily from Julia itself. So that part was actually quite manageable. Yeah, I don't have too much. I've done a bit of integration between Python and C++, but that was kind of on a very different setup. So I can't really qualify much on the differences between the two. So apologies about that.
Okay, thank you very much. That was perfect. Thank you.
No worries. Thank you for your questions.
Thanks, Yuri. Thank you, everyone. Great to have you here. And thanks, Dan and Devaraj.
Thank you, Alden.
Bye.